Chapter 12, Deflection of Beams and Shaft, Part A, Formula Derivation. Just consider we have a two simple support beam by a uniformly distributed load of W, which you can see at the figure at the top, and we have the same kind of loading and beam, but this time with a two fixed support at both ends. We want to know which of them has a larger delta maximum at its center. So by an intuition, uh, case 1 may have a bigger a delta maximum due to having a more flexible support in comparison to the fixed support. So let's get back to it later on. If we want to know the effect of a bending, so again, what you can see at the top is a maximum. It's a positive moment which pushes the top. The effect of a positive moment pushes the top and pulls the down, and vice versa for the effect of a negative moment on a cross section. So that pulls the bottom and pushes the top, pushes the bottom, pulls the top and pushes the bottom. So let's uh, go back to a reminder of dynamics to in a curvilinear motion in normal and tangential component. That's ut stands for tangential and un normal vector for a normal, it's to the center. Mhm. So, and if we can connect that to the rho and 1 over rho, which is a radius of curvature, and curvature itself, it's a good hint for derivation of our formula. So again, that's rho is a radius of curvature in a beam deflection, and 1 over rho is the curvature itself. So again, just consider we have a velocity which x is displacement, v is a derivation of displacement, that is r dot, and acceleration is r double dot, and we are interested in the tangential component of velocity. But how that goes? So tangential velocity, tangential component of velocity is the component which at any instant of time is tangent to the path itself. So v, vector of v, is just the numeric value of v times ut. So if that's our path, ut and u prime t are the tangential component of velocity. And at the same time, v is a derivation of the uh, x, or so that's s dot or y dot. So, and at the same time, acceleration, it has two components as well, and that's a tangential and a normal. And an, if we are driving our car in a circle, you can easily see normal component of acceleration is v squared over rho. And at, tangential part, is just a derivation of velocity though. So, and the numeric value for acceleration is a square root of t, at, a square root of uh, uh, normal, and just at squared plus an squared, a square root of that. That's our acceleration. And if in our example 1, we want to show that the curvature of radius in a curvilinear motion goes by this equation. So let's see how that goes. Again, r is displacement, v is a derivation of that r dot, and at the same time v is vut, and a is atu, at times atut plus anun, and and that's a, also we can say that a t is v dot ut plus v squared over rho times un, which we just showed in the previous slide. So v cross product a is vut times v dot ut with just replacement from here, and it just comes from here. That's a cross product. And that's a v cubed over rho times un. And how that goes, if you remember from a cross product rule, I cross product j goes by k in a counterclockwise condition. So what that says if I you cross product I to j, it gives you k in a counterclockwise rotation, and j times k gives you I. This is j times k give you I, and at the same time k cross product I, k cross product I gives you j. And at the same time I cross product I goes by 0, j cross product j goes 0, likewise k cross product k goes 0. In our case, if ut is a normal uh, unit vector, that's a cross product ut that goes by 0. So this part goes 0, and we just have vut times v squared over rho un. And if you mind, that can go also by u, for example, p, because that's a un times ut. But as far as we are working with the absolute value of the cross product, we do not need to be we do not be care. Uh, it doesn't matter. The unit vector is not the it's not a big deal. So how that goes? Then it just says v square absolute value of v cross product a is v cubed over rho. Rearrange the equation in base of rho, and it just gives you a v cubed over absolute value of a v times a. So v cross product a, and if you compare that, that's exactly our statement at the top. Let's review another example. So in this example, we want to show 1 over rho, or curvature is follows this is equal to this a second degree nonlinear equation. So how that goes? If we already know displacement is xi plus yj in a 2D dimension. V is r dot and just goes by x dot I plus y dot j, and a is r double dot and goes by this statement. From previous example, we just know that rho goes by this equation, and if we just rearrange that equation based off 1 over rho, it just uh, cross absolute value of v cross product a comes at numerator, and v cubed go to denominator. Let's work at the numerator. V cross product a, it just comes from this part, r and v, v and a, and again I, the component of I cross product I goes by 0, and it just gives you x dot y double dot k minus y dot x double dot k. And again, because we are working with the absolute value, forget about the normal unit vectors. So denominator, it just gives us velocity is x dot square plus y dot square root of that. And if you want to have v cubed, just make a cube of that. So that's x uh, dot square plus y dot square to the power of 1.5. If we call it c, b, and a, by simply replacing b and c in a, we can have a 1 over rho, which is x dot y double dot minus y dot x double dot over x dot square plus y dot square to the power of in parentheses to the power of 1.5. So step 1 is we need to create our numerator, which is this part. And that's d squared y over dx squared. And at the same time, we do know y dot over x dot, a variation of uh, y over variation of x is exactly dy over time variation of over variation of x over time. So if you cancel dt in both sides, it gives you dy over dx. And at the same time, the square y over dx squared is just d over dx of the same term from here. Mhm. d squared y over dx squared, you can replace it like d over dx, like y dot over x dot, which we already uh, calculate that. And you, by the rules of change, by the rule of chain, you can replace d over dx like this: d over dt times dt over dx, that's d over dx of y dot over x dot. So in that sense, you can easily cancel dt by dt and you get the same term. And at the same time, dt over dx is 1 over x dot. And at the same time, for this part, y dot over x dot, it just goes by a derivation of numerator times the denominator. So that's y double dot times x dot minus the derivation of numerator, which is x double dot times denominator times numerator over our denominator square. So that's x dot squared. So if you replace that, it just gives you d squared y over dx squared gives you this term. If we call this equation 1, mhm, uh, we already have, if we call it equation 1, we already developed a statement for dy squared over dx, d squared y over dx squared, which is over here based on the component of x and y. So the other part is step 2 is developing an equation for denominator, which is this part. And at the same time, we do know x dot square plus y dot square. If you can easily write the equation like x dot square in plus open parentheses, you can easily cancel this part, and that's again y dot squared. We just add that in terms of our derivation. So that's a, we can call this part, that's a y dot over x dot in parentheses squared, that's dy over dx squared. We observed it in previous slide. So in that sense, one can say it's equal to, if you factor out a x dot square, it just x dot squared times open bracket 1 plus dy over dx in parentheses squared. Hmm? And if you want to make that a to the power of 1/3, 1 and a half, you can just say x dot squared to the power of 1 and a half times 1 plus dy over dx, and that's a d over dx to the power of 2, then to the power of 1 and a half. That's to the power of 2, then to the power of 3 over 2. And that gives you x cubed over, that gives you this equation. And if we call that equation 2, and that's a close enough to our denominator. Mhm. 1 over rho, it just numerator comes from equation 1, denominator comes from 2, and if you cancel x dot cubed for both part, both numerator and denominator, you can get the same exact term of here. Hmm? So that says 1 over rho is d squared y over dx squared over this term. Mhm. And one can say dy over dx is a derivation of y in a beam is small enough in comparison to y, and that's the square root of that. It's a relatively small, or you can almost neglect it as negligible amount that goes zero in comparison to one. So in that terms, one can say a 1 over rho is a by by dy over dx squared goes 0, a nonlinear second order differential equation, which is not easy to solve at all, goes by an easy equation because dy over dx, as I told you, is very small. Then the square root of that is in comparison to 1, which is here, it's pretty negligible. So in that term, a nonlinear second-order differential equation turned to a simple equation of 1 over rho and is equal to d squared y over dx squared. Things getting more interesting when you can combine it with the material of chapter 6 of this books, which is a bending. And we know from bending these equations and a final result of this calculation in chapter 6 is 1 over rho curvature is m over ei. If you remember this equation from chapter 6, so combining chapter 6 with dynamic and chapter 12 of mechanics of material, it gives us a equation of again this is rho radius of curvature and 1 over rho is curvature itself. So it says by our calculation, if 1 over rho is equal to d squared y over dx squared, and at the same time 1 over rho is equal to mx over ei, so one can say, wow, d squared y over dx squared is equal to m over ei, and that's pretty interesting result, which just says if you have if you have the equation of moment for a beam or shaft, that's a d squared y of dx squared that's equal to a elastic curve of that beam. So how that goes? So let's say if we want have equation of elastic curve, let's first part from the moment. Mhm. If you look at this part, and if dy over dx is of tangent of theta, and that's a if theta is pretty small, tangent of theta is equal to theta itself. So, and at the same time from the previous calculation, we get d squared y over dx squared is equal to mx over ei. So if we just take the ei here, and make an integration of that, it just says having integrating the equation of moment gives us a ei dy over dx, and we just get that dy over dx is equal to theta, so we can call that a theta. So it just says area under m over uh, area under moment gives the slope, and if you integrate it once more, it just gives you a elastic curve deflection, or ei y or ei delta is a double integration from moments. So it just simply says by two consecutive integration from moment equation, we can get the deflection amount. And that's all for today. In next video, we just go to a sample of more example for a deflection of beam. Thank you.